we're going to begin by taking a look at your homework handout. So if you would go and take your handouts out from last night. Just 3 problems to do for homework. And the first, I gave you a square called ABCD. And I had a random, well, not entirely random point X marked here on AB. Lines were then drawn. Now, these are not diagonals, of course, but lines were drawn from D to X and C to X. And I told you that the area of the square ABCD was 81 inches squared. And I mentioned that X isn't an entirely random point. X is chosen such that AX is to BX as 2 is to 1. In other words, these 2 segments are in ratio 2 to 1. Well, if they're in ratio 2 to 1, how might I represent these 2 pieces? Genesis? Right, I could call them 2x and 1x if I so desired. And then the question is, what is the area of triangle ADX? Well, let's start with the first piece of information. If you know a square has an area of 81 square inches, that should tell us how big each side would be. Genesis? 20.25. Now, the perimeter is 81. The area is 81. What's the formula for the area of a square? So how do I find the length of the side? I don't divide by 4, I take the... okay, so how big is each side of the square? 9 inches. There we go. How many found each side of the square to be 9 inches? Now, what that means, class, is that AB is also 9 inches. And AB is 2x and 1x. In other words, we could say AB, class, is 3x, right? So it's 3x and it's 9 inches at the same time. So therefore, the 3x is 9 inches. How big is x? 3. So how big is this piece AX? 6 inches. And of course, BX is only 3 inches. How many found these 2 segments to be 6 and 3? Now, technically, you could have done it without algebra, right? You could have said, well, I know it's 9, and the only way to split 9 so that one piece is twice as big as the other would be to say 6 and 3. You could have kind of figured that out just logically, but here's the algebra mathy way to figure it out. We're now ready to move on to the area of triangle ADX. Now, ADX isn't just any triangle. ADX is specifically, Ethan, given that it's inside a square,
right triangle.
It's a right triangle. And how do we find the area of a right triangle, Ethan?
BH.
Well, any triangle's BH, but more specifically, a right triangle would be
Leg 1, leg 2.
half leg 1, leg 2. Well, that works out pretty nicely here because, Ethan, how big are the 2 legs?
6 and 10.
Say what?
Oh, wrong. Sorry. 9 and 6.
9 and 6. Where we can, of course, take half of 6 class to get
33.
and then multiply that by the 9 to get what for the area of the right triangle ADX? 27. Is that inches? Inches squared. How many had 27? Square inches for your answer. All right, a few of you did. Those of you who didn't, questions. Questions. Do we see it now? Going once on questions. Twice on questions. Gone on questions. All right, let's take a look at problem number 2. And here we started off with a parallelogram, ABCD, and I gave you once again the area of the entire figure, much like we did in the last problem with the area of the square. So given the area of parallelogram ABCD is 160 inches squared, and given that side AB, which we would call, class, the base of the parallelogram, is 16 inches, remember that's the base, and given that DX equals BX, we can find the area of triangle CBY. By the way, have any of you ever been to TCBY?
What is that?
The country's best yogurt. It's a frozen yogurt place. It's been around for forever. Anyway, so I don't know if you caught the TCBY. I didn't. Anyway, but anyway, so we've got this.
Yeah.
We've got this parallelogram here, and we know the entire base is 16 inches. And I know there's this perpendicular. Did I give you two? I actually gave you two perpendiculars. Okay, so I gave you both of them. And we said that dx equals bx. And that's in A, B, C, Y, D. Well, let's just take these two thoughts. If I know the area of a parallelogram, and I know that the base is 16 inches, then Jamie, I should be able to find the
area of the...
Well, I know the area of the parallelogram, but if I know the area of a parallelogram and the base of a parallelogram, I should be able to find the altitude using the formula.
PL equals PH.
Yeah, if you're ever stuck on a problem, go to the area formula for whatever figure you're dealing with. This is a parallelogram. Go to the area formula, plug in your 160 for PL, plug in the 16 for B, and then you're going to find H class to be 10. How many found the altitude to be 10 inches? All right, so that's right here, that's 10 inches. Well, remember, it said that dx and bx were equal. What that means is that right here, bx is also 10 inches. But remember, the whole thing, AB, is 16 inches. Thoughts, Quentin?
AX will be 6 inches.
AX is going to be 6 inches. But if these two lines are both perpendicular to parallel lines, what's true about the two auxiliary lines I gave you, Audrey? You're actually one step ahead of me. They're at least parallel, right? Because they're perpendicular to parallel lines. Two lines perpendicular to parallel lines are parallel to each other. And since it's a parallelogram, these are now parallel lines included between parallel lines, so they are equal. Which means this line class is also 10 inches. And by the way, bx and dy are parallel lines included between parallel lines, so dy has to also be class 10 inches. Hopefully you recognize that's a perfect square. How many did recognize a perfect square 10 inches all the way around? Well, what that means is if AB is 16, then class DC is 16. So if dy is 10, cy must be 6 inches. Another way to think of this is these two triangles have to be congruent to each other. That's what happens when you come down and up from the respective vertices. So when it says find the area of triangle CBY, once again you might ask yourself, what kind of triangle is CBY, Chris?
Right.
It's a right triangle. And how do I find the area of a right triangle, Genesis?
1/2 leg 1 2.
There we go. But I know the two legs, Genesis, so in for L1 and L2 I could plug in.
10.
Well, the legs of this triangle are not 10 and 10, but 10 and 6. There we go. And I would take half of 10 to get, and 5 times 6 is 30 inches squared. How many did have 30 inches squared? Now there's another way you could think about it. Remember I mentioned these are congruent? And we already know this is 100 square inches in here, correct? 10 by 10 squared. If there's 160 inches squared, and 100 of them are right here, that leaves you 60 total remaining, right? Half of the 60 here, half of the 60 here, that's 30 and 30. And you can do it that way without even using the formula over there. So more than one way to figure it out. Questions now that we've seen it from those who did not get the correct answer. All right, let's take a look at the final homework problem. And this time you had a right triangle up against a square, almost like a ramp leading to the top of a stage or something. So here's the square, and we don't know the area of the square. In fact, that's what I'm trying to figure out. What is the area of BXYC, the square? And then I do know that this ramp line that comes down makes a 30-degree angle. Bing, 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 bing. Class, what should we be thinking? 3069. And I'm told that AB is 12 inches. I not only want to know the area of the square, I also want to know the area of the triangle. Well, if it's a 30, 60, 90, I should be able to represent its three sides. How would I represent this 12-inch side, Ethan?
X times square root of 3.
Right, it's across from the 60-degree angle. It's x times the square root of 3. How would I represent this side right here, BC? Jamie?
X.
X. It's the little one across from the 30. And then how would I represent AC, this hypotenuse here, Genesis? 2x. Now, if 12 is x times the square root of 3, or 12 equals x times the square root of 3, we could say, then if I wanted to find plain old x right here, what would I have to do, Chris?
Make it 4 over 3, or 4 times square root of 3 over
Well,
3.
divide away the square root of 3, right?
Yeah.
And when I do, I get 12 divided by square root of 3. Of course, we know that's no good, so I need to rationalize by multiplying top and bottom by.
Square root of 3.
And when I do, now my numerator becomes.
12 times square root of 3.
And the denominator becomes square root of 3 times square root of 3, or in other words,
Square root of 3. Or square root of 9.
which is
9. 3.
3. There we go, becomes the square root of 9, which is 3. And then, Chris, we can do a little bit more reducing here.
3 goes into 12 4 times, so 4 times square root of 3.
And so x comes out, well, not evenly, but at least it's not a fraction, to 4 times the square root of 3 inches. How many found BC to be 4 times the square root of 3 inches using the 30, 60, 90? If not, you couldn't do the rest of the work. Does it make sense now? Just be careful with your algebra. By the way, I don't care about this line AC, as it turns out, but how long is it, class? 8 times the square root of 3 inches. It just really doesn't matter. Because the two figures I'm finding are a square and a triangle. Specifically, what kind of triangle, class? A right triangle, where I know the area of a right triangle can be found using the formula, class.
1/2 leg.
Half leg, leg. You could say a half base times height. There's the base, that's one leg. There's the height, that's the other leg. And it really didn't matter. And so we'll just multiply. Half times 12 times 4 square root of 3. Let's take half of the 12, class.
6.
Times 4 times the square root of 3.
24 times square root of 3.
And we're dealing with inches here, so inches squared because it's an area. Now the square, on the other hand, is a totally different formula. What's the formula to find the area of a square, class?
S cubed plus S squared.
Side squared. Well, I know that a side is 4 square root of 3, which means all of them are 4 square root of 3, right? All the way around. So that means we're going to take 4 times the square root of 3 squared. Remember, when you square a radical, you'll square the coefficient to get
16.
and you'll square the square root. Go back in your mind to your algebra days. When you square a square root, you get the radicand. Say that together by way of review, especially for those who haven't did Algebra 2 yet. When you square a square root, you get the radicand. Again, when you square a square root, you get the radicand. Kendall, I can't hear you. Let's try that again. When you square a square root, you get the radicand. So when I square the square root of 3, class, I get 3, because that's the radicand. In other words, the square and the square root cancel. And 16 times 3? 48. And so I get 48 inches squared for my area. How many had 48 square inches for the area of the square? A couple of you. How about 24 times square root of 3 inches squared for the triangle? All right, a couple of you there as well. Questions from those who did not?
It seems like if I multiplied both my answers by 3, I would have gotten both of them.
Okay.
because I would have had 24 times square root of 3, and I would have had 48 inches squared. But I had 16 inches squared and 8 times square root of 3 inches.
All right.
I don't know.
Questions on this? All right, set your homework aside if you would, and let's go and review over the theorems that we talked about yesterday. We started by discussing a couple of triangles that weren't even similar to each other, but they did at least have one angle of the one triangle equal to one angle of the other triangle. And so if those two angles are equal, again, the triangles aren't similar, I don't care about that, but if this angle equals this one, then we said that the areas are to each other as
The product of the sides.
the product of these two sides. Now again, these sides are not equal, but, well, let me mark them like that then. But the product of these two sides compared to the product of these two sides is the same ratio as the areas of the triangles. And then we said, well, let's go a step further then. Let's go ahead and take a couple of triangles that really are similar to each other. And we said if triangles are similar to each other, then area is to area, someone besides Chris this time, area is to area as okay, Chris.
The sides that make up the vertex angle?
Well, it doesn't have to be the product of the sides because they're similar triangles and sides are already proportional. We're looking it up now in our notebooks because we don't remember. Call it out. The square of any side to the square of the corresponding side. So we can take these two sides, these two sides, these two sides. It doesn't really matter. Area is to area as any side squared is to the corresponding side squared. That's where we left off yesterday. Theorem 74 in your notebooks now. Theorem 74 in your notebooks now. That's triangles. But that's kind of limiting if all we have is triangles. What about other polygons? Well, keep in mind, if two polygons are similar, then they can be broken down, remember, into the same number of triangles. These triangles will be similar each to each and similarly placed. And for each of these sets of similar triangles, area is to area as side squared is to side squared. Area is to area as side squared is to side squared. Area is to area as side squared is to side squared. But all of the side squares are the same ratio because the polygons are similar and sides are proportional. So therefore, the area of the whole thing will be to the area of the whole thing as side squared is to side squared. Same as what we just talked about, but it's not only true for triangles, it's true of any similar polygons because similar polygons can be broken into triangles. So, Theorem 74, the areas of two similar polygons, the areas of two similar polygons are to each other. The areas of two similar polygons are to each other as the squares of any two corresponding sides. The areas of two similar polygons are to each other as the squares of any two corresponding sides. So one might say that area is to area, side squared is to side squared. But think about this for a minute. Remember we said the ratio of any two corresponding sides. We call that class the ratio of similitude. But there was another ratio we said a while back was the same thing as the ratio of similitude. And that was the ratio of the...
Ratio of the proportion? No.
Of the perimeters. Remember we said perimeters to perimeters, side to side, right? So in that case, corollary 74-1, since the areas are to each other as the squares of any two corresponding sides, we could also say, Theorem 74-1, the areas of two similar polygons, the areas of two similar polygons are to each other, the areas of two similar polygons are to each other as the squares of their perimeters. The areas of two similar polygons are to each other as the squares of their perimeters. The areas of two similar polygons are to each other as the squares of their perimeters. If you would, go back to your class notes section of your notebook. And let's kind of summarize these last few theorems. Find that area formulas page that you have. And let's talk a little bit about similar polygons. What do we know about the areas of similar polygons? Well, we know this, that the ratio of areas equals the square of the ratio of similitude. After all, the ratio of perimeters is the ratio of similitude, and we said the ratio of areas equals the square of the ratios of the perimeters. We said the ratio of similitude is defined as the ratio of any two corresponding sides, and we said that areas are to each other as the squares of corresponding sides. So we know that the ratio of areas equals the square of the ratio of similitude. But let's quantify that more in an equation form. Let's put that more in an equation form, and we'll say it this way, that area is to area as side squared is to side prime squared. So A is to A prime, as S squared is to S prime squared, as P squared is to P prime squared. And this is a formula we can use anytime we have similar polygons. Area is to area, as side squared is to side squared, as perimeter squared is to perimeter squared. Say that with me, class. Area is to area, as side squared is to side squared, as perimeter squared is to perimeter squared. Again, area is to area, as side squared is to side squared, as perimeter squared is to perimeter squared. And again, this is true when the polygons, class, are similar to each other. Let's take this problem, for instance. Let's suppose we have a couple of pentagons that are similar to each other. Suppose I know that this side is 12 inches, and I know that a corresponding side is 8 inches. At your seats, what is the ratio of similitude? Jot it down maybe on a scratch piece of paper somewhere. What is the ratio of similitude? You don't have to draw the figures necessarily, just writing down our answer here. Though if you want to try to draw the pictures, more power to you, I suppose. We have two similar pentagons. Two corresponding sides happen to be 12 inches and 8 inches. What's the ratio of similitude, class? Class. My 8th graders know this. What's the ratio of similitude? 12 to 8. It's the ratio of any two corresponding sides. But we wouldn't leave 12 to 8, right? We would reduce it down to
4 and 2. Right. 3 is 3.
3 to 2. That's the ratio of similitude. Any two corresponding sides make a ratio out of it. Let's try this. What's the ratio of the perimeters? I don't even know the perimeters, but I can tell you what the ratio of the perimeters is. Write it down. What's the ratio of the perimeters? Class? 3 to 2. Remember we said the ratio of the perimeters is the ratio of similitude. It's the same thing, same ratio. What's the ratio of their areas? Now I don't know either of their areas, but I can tell you what the ratio of their areas is. Class?
3 to 2.
The ratio of areas is the square of the ratio of similitude. 9 to 4. Do we see the relationship between ratio of similitude, that's sides, perimeters, it's the same thing, and areas is simply the square of the other. Does that make sense? Let's do the same exercise with different polygons now. Let's suppose I have this triangle similar to that triangle. And suppose I know that this triangle has a perimeter of 32 feet. And suppose I know that this smaller triangle has a perimeter of 20 feet. Class, write it down on your paper. What's the ratio of the perimeters?
8 to 5.
Class,
8 to 5.
8 to 5, right? We simply reduce down the ratio of the perimeters. Class, what's the ratio of similitude? 8 to 5, because the ratio of similitude is the same thing as the ratio of perimeters. What's the ratio of their areas, class?
64 to 25.
Good, 64 to 25. It is the square of the ratio of similitude and perimeters. Does that make sense? Are we seeing the relationship? Let's do one more, and then we'll go to some word problems. Let's suppose that I have a couple of weird-looking quadrilaterals.
What is that?
It's a big nothing. It's almost a trapezoid. Let's suppose these are similar, and suppose I knew the area of this first polygon is 81 centimeters squared. Suppose I know that the area of this one is, let's just say, check that, 121 centimeters squared. Let's call this one 81 centimeters squared. Class, what's the ratio of their areas?
11 to 9. No, it's 121 to 81.
The areas are 121 and 81, so the ratio is 121 to 81.
Pull a fast one.
Make sense? What's the ratio of similitude? 11 to 9. It would be the square root of the ratio of areas. What's the ratio of perimeters? 11 to 9. It's the same as the similitude. It's the square root of the ratio of the perimeters. Questions on that? We understand how all this works. All right, let's take a look at some problems here then on the PowerPoint. Give me just a minute to get the camera set for it though. And we'll get the time for the screen to warm up here. You can set your books aside at this point. You don't need those anymore. Now let's go and take a look at the first problem together. Go and read it for us nice and loud if you would, Quentin.
Corresponding sides in two similar hexagons are 5 inches and 9 inches. If the area of the second hexagon is 162 inches squared, find the area of the first hexagon.
All right, let's start with our formula that shows the relationship between areas and sides, right? What's the ratio that shows the relationship between areas and sides of similar figures, class? Area is to area as side squared is to side squared. Now, it does keep going as perimeter squared is to perimeter squared, but there aren't any perimeters in that, so I don't care. I ain't going to write it. I'm too lazy. And we just plug it in. So at your seats, plug in the numbers. And what do we get for the area of the first hexagon, class?
50 inches squared.
50 inches squared. Did you plug it in correctly? Did you say A is to 162, that's the area of the second, as 5 squared is to 9 squared? Squared, we get 25 and 81, and just cross multiply on your calculator. Questions?
Yeah.
Let's take a look at another one. I'm going to read this one for us, Ethan, nice and loud.
The areas of two similar pentagons are 64 feet squared and 225 feet squared. If one side of the first pentagon is 12 feet, find the corresponding side of the second.
What proportion should we use here, class?
Area to area, side squared, side squared.
Yeah, areas to areas, side squares to side squared. At your seats, plug it in, set it up, find it. 225, I can't copy. Does help to copy the problem now, right?
Just like that,
Okay, scaring me again. All right. All right, I was a little slower this time since I messed up. I wrote down a 125 for some reason after I wrote 225. How many got 22 and a half feet? 22 and a half feet. Again, you say 64 is to 225 is 12 squared is s prime squared. Now realize, don't lose that square, that's important, so that when you cross multiply, that's a 64 s prime squared, which means we have to take the square root at the end. There is a quicker way though. If the areas are 64 and 225, then obviously class, the ratio of the areas is 64 to 225. So what's the ratio of the sides? 8 to 15. So 8 to 15 is the ratio of the sides. Not the ratio of the sides squared, just the ratio of the sides. And since one side is 12, what's the other side? Do you see that's a little bit quicker? Another way to think of it would be this. Remember the power root transformation? 8 is to 15 is 12 is to s prime. You could also have done that. So instead of dealing with massive numbers like I showed here, which is the natural way to do it, we can make our life easier. Questions on that? Let's take a look at another one here. Go and read this one for us if you would, Genesis. Nice and loud.
Two similar triangles have perimeters of 15 inches and 25 inches. The first triangle's area is 18 inches squared, and the area of the second triangle.
All right, I'm not even sure if these numbers are possible, but we're going to roll with them anyway. What proportion should we use here since we have perimeter mentioned and area mentioned, class? Area is to area as perimeter squared is to perimeter squared. At your seats, solve.
I see an easier way.
There is, I'm going to show it in just a minute.
Okay.
There is a bit of a shortcut you could use here. I'm showing the natural way to do it, just plugging into the formula. There's a way you could do this just thinking logically a little bit. How many got 50 inches squared for the answer? Now, here's the thought. If the perimeters are 15 and 25, what's the ratio of the perimeters, class?
15, 25.
15 to 25, or reduce it down to 3 to 5. That's perimeters. So therefore, what's the ratio of the areas, class?
9 to 25.
9 to 25.
25, yeah.
And if the ratio is 9 to 25, and one area is 18, what's the area of the other? Well, you could just do the equal ratio method times 2 to get you 50. So you can do a lot easier math thinking it through that way. But again, the formula works, plugging in the numbers. You have a calculator. It does the work for you. Questions on this? All right, we will pick up with more of these problems in our lesson tomorrow. No homework this evening other than make sure you're studying over this as you always do. Make sure you're studying formulas, memorizing them, being ready. Because we have a test coming up Wednesday. Test coming up Wednesday, that's in lesson 167 over all things area, as well as some of those constructions that we did a little while back with the mean proportional and the third proportional and similar polygons, all of that. So test coming up Wednesday, lesson 167, and we'll be reviewing for that on Tuesday of next week. Got a couple more days to finish up content here, but no homework this evening. Have a wonderful rest of your day, and you are dismissed.